In the previous videos, we've talked about the derivative of sine and cosine fairly extensively. In this video, I'm going to do some examples with other trig functions and then possibly using the product and quotient rules with those trig functions. But before we do that, I would like to talk about the proof of the derivative of tangent. So one thing that we learned that we decided we were going to memorize is that the derivative of tangent x, the derivative of tangent x with respect to x, is going to equal secant squared x. So this is something that we store, we know, we're going to keep for the rest of our mathematical career. So let's talk about how we know that. Well, if we think about our function y equals tangent x, what you want to remember from trig is that tangent is the ratio of sine x over cosine x. So this is a quotient here. So if we went to find the derivative, we would say that y prime or dy dx, using our quotient rule, remember quotient, the derivative with respect to x of some numerator over a denominator, is denominator numerator prime minus numerator denominator prime all over the denominator squared. So here we have to use the quotient rule, and we're going to have cosine x. Right here we would have the derivative with respect to x of sine x, and we know what the derivative of sine is. The derivative of sine is cosine. So times cosine x minus the numerator, which is sine x, times the derivative of the denominator. And the derivative of cosine is negative sine x. That would be all over the quantity cosine squared x, cosine x squared. Just a note, writing cosine x quantity squared is the same as the way I've written it here with the cosine squared x. All right, it's just a abbreviated or a nicer way to look at it. So here we have in the numerator cosine squared x, and these two negatives, negative, negative, that becomes positive sine squared x, all over cosine squared x. When we're dealing with trig functions, we always look for identities, and sine squared x plus cosine squared x, that is my Pythagorean identity, that's equal to 1. So here I have dy dx equals 1 over cosine squared x. And that is secant squared x. Remember, secant is reciprocal to cosine. So therefore, the derivative with respect to x of tangent x is secant squared x. All right, let's do another example or two in this video. Here, we're asked to differentiate y equals secant theta times the quantity sine theta plus cosine theta. Now, most of you would look at this and say, all right, I need to use my product rule, which would be first secant theta times the derivative of the second, that would become cosine minus sine, plus the second times the derivative of secant. And the derivative of secant is secant times tangent, secant theta times tangent theta. And that would be perfectly fine. And we end up using a lot of trig and algebra properties to simplify it. However, what would happen if I took this secant theta and distributed it? That would give me y equals secant theta sine theta plus secant theta cosine theta. What I want you to remember now is that secant is 1 over cosine. So this is the same as writing sine theta divided by cosine theta, because secant's 1 over cosine, plus cosine theta divided by cosine theta. sine over cosine. That gives me tangent theta, and cosine over cosine, that gives me 1. Now, I haven't done any calculus yet. This is all still the original function. All I've done is use my trig properties and what I know about trig to simplify this. At this point, if I were to go and take the derivative of y, in this case with respect to theta, the derivative of tangent is secant squared theta, plus the derivative of 1 is 0, which we do not need to write. So this example just goes to show if you are comfortable in your trig, the calculus is really, really very simple. So whenever we can, we want to try and simplify first. We could, again, work this out using our product rule. We would just have a lot more steps in the middle. So this really abbreviated the problem for us. Let's do another example. For our last example in this video, we're going to differentiate P equals Q times the quantity sine of Q divided by the quantity Q squared minus 1. So we've got a lot going on here. There's a little bit to unpack. What is occurring between Q and sine of Q? What we notice is that is a product. So when I take the derivative of my numerator, I'm going to make sure I use the product rule. And then we have this divided by another expression. So that lets me know, because I have a numerator and a denominator, that I'll need to use my quotient rule. So we're going to use both of those rules in this problem. Now, when I look at this, P equals Q sine Q divided by Q squared minus 1, it's not immediately evident to me, something that I should be able to do to simplify it. I don't really see something. I do notice that this is a difference of squares, but factoring it in this situation is only going to give me more to work with. So it's easier in this case to leave it multiplied out. All right, so let's begin with our derivative. The derivative of P with respect to Q, that is my denominator, Q squared minus 1, times the derivative with respect to Q of my numerator, which is Q times sine of Q. Now, when we're using the product rule, we have a minus, so that would be minus the numerator, Q sine Q, and then we have times the derivative with respect to Q of Q squared minus 1. All of this is over that denominator, Q squared minus 1 quantity squared. So I have two derivatives inside this quotient rule, which I've applied here, that I need to take. The purple one, Q squared minus 1, this is easy. This is just going to be 2Q when I differentiate it. But Q times the sine of Q, I'm going to need to use the product rule. So this might be a situation where I do this off on the side or in a separate situation. I'm just going to put here that's going to equal 2Q. So I'm going to do my scratch work for just this part. So that derivative, the derivative with respect to Q of Q times sine of Q, that equals Q times the derivative of the second, the derivative of sine Q is cosine Q, plus sine of Q times the derivative of Q, which would be 1. Right, so I don't need to write that 1 there. So I have dP dQ equals Q squared minus 1. This derivative turned into Q cosine Q plus sine Q we have minus q times sine q times 2q all over the quantity q squared minus 1 squared. Okay, so at this point I'm done taking my derivative. We just need to use a little bit of algebra to simplify. For my first step, I have this big multiplication here. I'm going to FOIL first, outer, inner, and then last. And what that gives me is dp dq equals q cubed cosine q plus q squared sine q minus q times cosine q minus sine of q. And this last term here, that's going to be 2q squared sine q, and it will be negative. So I have minus 2q squared sine q. Again, all over that same denominator, q squared minus 1 quantity squared. So what we'll notice is I have 1q squared sine q minus 2q squared sine q. Those are the same. I can combine like terms. I would have negative one of those. Nothing else is going to simplify here, so I will leave this as dp dq equals q cubed cosine q plus 1 minus 2, that would give me minus q squared sine q minus q cosine q minus the sine of q, all divided by q squared minus 1 quantity squared. And at this point, I look to see if I can factor, maybe using grouping. And if I factor out a q squared and a q, if I factor out a negative 1, that would give me a positive q. We would still have the wrong sign here, so we can't factor it any further. In this situation, this is my final answer. So I hope that gives you guys a little bit more practice finding derivatives of trig functions.